мелок у нас 10 все мелкие.
Сейчас я проверю, что звук есть.
Hello. Раз. Работает.
Да, так что?
By the way, are seminars graded in some way or not?
No, seminars are not graded, but attending seminars is very instructive.
Okay, first problem is let f and g be multiplicative arithmetic functions. So these are functions from natural numbers to, for example, to complex numbers. And we know that they are multiplicative. Do you know what multiplicative means? Yes, from lecture we know that it means that f of mn is f of m times f of n, but we need condition that m and n are relatively prime. Okay, and we need to prove that such Dirichlet product, yes, is also multiplicative. I think everyone can do this problem by hand, but let me introduce. You all know what Dirichlet series means? Yes, formal series, and yes, and you have criterion. So maybe you can, someone can do this problem instantly. Okay, can we?
We did not check is that this product corresponds to the product of Dirichlet series. So maybe someone should go and check that this corresponds to the product of Dirichlet series.
Okay. No, n to n to s. Yes. I think we have n and n in both cases. Like when you multiply polynomials, you have one formal variable. No, yes, sorry. S is formal variable, yes, and here you could write m, sorry.
So we transform the product.
Mm-hmm. We checked this criterion on lecture, I think, and now we just check that when you multiply Dirichlet series, you have such operation. Yeah, yes, yes.
Еще раз, можно пояснить переход, который вот самый первый раз, почему у нас именно такой суммирование?
Вот, значит, вот так можно писать. Значит, еще что вот здесь появится при вот таком знаменателе. Здесь появится вот это.
Меня скорее интересует именно суммирование.
Значит,
Которое под второй суммой.
значит, ищем все попарные произведения вот тут, у которых знаменатель будет вот это. У этих знаменателей произведения этого, ну и вот тут вот с все. То есть ищем все такие пары, у которых произведение вот этих равно вот этому.
Okay. Okay, and maybe now you can solve problem 1. If we know that f and g are multiplicative, we need to prove that this is multiplicative. Just use the criterion from lecture.
So what did we prove here?
We prove that if we for f and g we have corresponding Dirichlet series, yes, and Dirichlet series for this function is just the product of Dirichlet series, yes.
Always. For any.
Yes, always. Just open the brackets.
So this is the Dirichlet series for the Dirichlet convolution, right?
Yes, yes. This function multiplied by k to the power s.
So what did we prove it equals to?
We prove that this f Dirichlet product with g of k is sum of all divisors of k f of n multiplied by g of n. Okay, I can repeat. Oh, okay. Yes, and we have the same for g. And then we just multiply these two products and yes, we have product over primes. No, all primes. Why pairs? This is product, so just product over primes. This bracket and the same for g. And this is Euler product for our Dirichlet series, so corresponding function must be multiplicative. Is this solution clear?
Here we never use that functions f and g are multiplicative, right? It's just a general.
Yes, this is general.
Yeah.
And multiplicative criterion says that f is multiplicative if corresponding Dirichlet series has Euler product. And we just multiply two Euler products and get another one. Okay, it's clear. Of course, we can open brackets, but it does not matter, I think. Yes, it will be 1 plus f of p plus g of p. Yes, we open brackets. What's the question again? What's the question? If you want, for example, to know f g of p, where p is a prime, yes? This is f of p plus g of p, of course. Because this is sum all divisors, and there are only two, 1 and p. Yes, so everything works. Okay? Okay, I think it doesn't matter. Next, maybe, thank you very much. Next problem. Do you know what is the sum of Mobius function? Yes, so maybe you can solve problem 2. Okay, please.
The square free integer is just an integer that just doesn't contain any powers, primes higher than 1.
Yes, or if it is not divisible by any square not equal to 1, full square.
Okay, so if n is in one direction, if n is square free, then it is just a product of some prime numbers. Well then, by definition, there are no squares other than 1 that divide n. So then g of n is just mu of 1, which is 1. So this is trivial. Now if n contains some primes of power higher than 1, and maybe some primes prime 1, which doesn't really matter. We can exclude these primes because, well, obviously, it wouldn't matter if they're here or not when we are searching for divisors that are squares. So we can just drop them. We are left with this, and now, absolutely analogously to the proof of the fact that if we leave it like this, without the square, we will have 0 for n bigger than 1.
And how you proved this on lectures? You mean inclusion exclusions? Or what?
Well, yes, we consider it. Well, this is just.
Okay.
Should I write this again?
Oh, no. Yes, maybe let me. Okay, I believe, yes, it works. Maybe let me tell you another, maybe the same solution. N has a square part, yes? It is like m square multiplied by d, where d is square free. And we want to know if m is, well, no, not dk, we have d. And we want to know if m is 1. And d square divides n is if and only if d divides m. Yes?
D squared divides n, if and only if d divides m, yes.
Yes. So this is just sum over divisors of m.
Well, this is basically this.
Yes, but we...
This is m in this case.
not m. We should look...
Some
yes.
could be,
Yes.
Let's say that all powers are even, and in case there are some odd.
Yeah, we can say that all these powers are even.
Yes. It's just the same proof. Okay.
And then, so these d squares are just not 0 are just e1 equals in the power of 2 and so on. K in the power of 2. And absolutely analogously to this case, we can prove everything is the same, just the powers are 2 instead of 1. So it's
Okay, thank you. Maybe you had a proof. Okay. With inclusion exclusion, let me tell you another short proof with Dirichlet series. You know there is a zeta function, zeta of s. Yes, yes. Oh, okay.
Просто не очень понятно, откуда у нас в конце. То есть мы взяли d квадрат некоторый, да?
Ага.
И, соответственно, что у нас дальше произошло за магия?
Значит, возьмем n.
Да.
n единственным образом представляет в виде произведения квадрата на бесквадратное число, правильно?
Да.
Вот. Но вот утверждается, что d квадрат делит n, тогда это только тогда, когда d делит вот эту квадратную часть.
Да.
Ну и что? Дальше получается, что мы суммируем μ от d по всем делителям векторного числа.
Так, а потом у нас...
Ну, если мы суммируем μ от d по всем делителям векторного числа, у нас получается единичка.
Все, понятно, да.
Okay. In this formula, it is 1 if d is 1, n is 1, and 0 otherwise. So another way to see this easily is that you know that zeta of s has such product over primes 1 minus 1 over p to the power s to the power minus 1. Do you know this formula? Do you have this on lecture?
I think it was given.
Yes? Just open brackets. Okay? And so what's the inverse of zeta function? I mean, this is product over 1 plus 1 over p to the power s, 1 plus p to the power 2s, and etc. So if you open brackets, you just see that this is sum over all natural numbers, 1 over n to the power s. And this is zeta function. And what is zeta function to the power minus 1? It has a Euler product. And what is it? You just, it's just product over primes, 1 minus 1 e to the power s. Yes? And if you open brackets now, you see that you have just definition of Möbius function. Yes? Who can see this? Yeah, yes. And now, so first fact is this. So who can understand it? Möbius function is defined just in this way. Mu of n, it should not...
So what is written here is that this mu of n should be a multiplicative function such that it is equal to minus 1 on primes and 0 on squares, cubes, and so on.
Yes.
Right? This is precisely the Möbius function I have defined on the lecture.
Okay. And from the our previous talk, we know that it's just 1 is equal to zeta of s multiplied by zeta to the power minus 1. And this means that this function 1, I mean a function which is delta, you mean
Small delta.
this one?
Symbol can make it.
Okay. This function, it is 1 on 1 and 0 otherwise. This is Dirichlet product of mu and function which is equal to 1 on every natural number. And it's just this formula if you look at the definition. Okay. Okay, problem 2 will be helpful in problem 4, I think. Now let's solve problem 3, and let me tell you what you can start from. This identity 1 is equal to sum over n less or equal to x, sum over d divides n, mu of d. Who can see that this identity is trivial? So that we already know this. Who can? Who do? Yes. Who does not understand? Who? Yes. I should write bigger letters.
Единица равна сумма по n превосходящему x. И дальше внутри сумма по t делящему n mu от n.
Yes, look at this formula.
Здесь написано одна единичка и куча нулей. В сумме одна единичка и куча нулей, тогда дают единичку. Счастье.
And now you should do a trick, change the order of summation. And
You can also assume that x is an integer.
yes, for example, but it's always true. Yes, change the order of summation.
No, this is only true if x is at least 1. If x is small, it's false.
Okay.
If x is smaller than y.
Ну, понятно, что можно проверить для нуля отдельно, потому что это пустая сумма.
We have two indices, d and n. I advise you to change. Yes.
But we still should change the order of summation to get at least something. So we need to turn the inner sum into the outer sum and vice versa. So now outer sum will be sum over d. If d is divisor of some number less than x, then what can be said about d?
About n.
Yeah,
Yeah.
d is less than or equal to x. And nothing else, right?
Okay, I'll give you some time, and you are welcome to tell the solution. Maybe one can walk and write on the board what.
To use Abel's summation.
Hmm?
We have to use Abel's summation.
What this means, Evels?
I did.
No, I don't think that this is the case. Problem 2?
I don't think.
I'm not sure. Maybe you can. Yeah, we now solve problem 3. We already solved problem 2. Mm-hmm. You can solve in another way, of course. Yes, you can do it on Blackboard. even if you do not have a solution. We can help you.
By the way, please write down what we are proving right now.
Okay.
We want to prove
Yes, this is good. We want to prove that for every x, sum over n less or equal than x, mu of n divided by n is less or equal than 1.
Yeah, so this is an interesting example. If you sum 1 over n, then you get a logarithm. And then to each n, you assign plus or minus sign and sometimes 0. And this sum experiences the parametric cancellation. So instead of logarithm, you get something bounded.
D less or equal than x. Yes, we can't have d more than x. Yes, yes, yes.
Предела нету. Условно. Бесконечно.
Угадаете? Предел существует.
Это не значит ноль.
Можете угадать, чему он равен.
Это был не значит ноль, это было просто...
Что еще раз?
Это был не значит ноль, это было просто какой-то...
Угу.
Сказать, что этот предел 0, это очень нетривиальный.
Oh,
Тут у нас множество одинаковых слагаемых. И вот...
yes.
Для каждого n мы должны посчитать, сколько существует таких n.
So here we have mu of d and we can write it here. Yes? Mu of d. Multiplied by the number of such n's. And it is equal to... Yes, yes, yes. Oh. I suggest you to write this integral parts like a difference of x divided by d minus fraction part. No. Okay, and now we see that we have this interesting sum, x multiplied by this interesting sum. So please write what it is equal x multiplied by this sum mu of d over d is equal to what? And in 1 here. Plus, I think. Yes. Sum over d. Over d. And Mobius function here. Yes, and the problem is equal to prove that this is modulo of this is less than 1, and so modulo of this is less than x. Can you see that modulo of this sum is less than x? Less or equal? We can assume that x is an integer. For example, maybe it's a bit easier, because yes, we need to prove this only for integers. And
Is it just saying that this is
Each summand is less than 1. Yes, module of each summand is less equal than 1.
Yes. And
But we have x summons, and we need x minus 1.
yes, but
But actually, we can exclude one of them or two of them.
if yes, if
Yes, if d is 1 or if d is x. Yes. Okay. Is the solution clear? Thank you. Yes, we have 1 plus here x summons. Yes. Each one with this is module of this is less or equal than 1. Actually, less than 1 always. Yes. And we have x of them, but I say that we can exclude, for example, d is equal to 1. In this case, this is 0. So x or less summons each has module less than 1. And absolute, sorry, yes, absolute value. And thank you. And it tells us that our sum, absolute value of our sum, is less than, for example, x, and it is enough for our problem. Yes.
Wouldn't we get 1 plus the sum? I thought we had.
Yes, 1.
Estimate mu of d by 1 and fractional part
By 1.
by 1. Then you get sum of ones over d less than or equal to x.
No, I mean before that. Why did we get 1 plus the sum?
Because 1 is equal to this, and we change the order of summation. We have this, and this is equal to mu of d, x over d. We can.
Я думаю, что между второй и третьей строчкой направо.
No, okay. Okay. Are there any other questions? Okay, let us move to the problem 4. Yes, we finally do something interesting. A, B, and C are somehow similar. D is a hard problem. Maybe we will skip it. Okay, problem 4A. We have K3 number. K3 numbers. And we want to find an asymptotic formula for K3 numbers below x.
What does it mean to find an asymptotic?
Yes, we want the main part and in some residue term, remaining term. Yes.
Basically, we want our mysterious function to be approximated by some easy function plus something bounded by something less than this easy function. For example, the number of squares below x is square root of x plus big O of 1. This is a nice asymptotic formula, right?
So we want to express it as some function plus big O.
Some nice function. What is nice is
Some nice function plus
is
big
of course
O.
undefinable.
So some nice function plus big O of
Or some other nice function.
And do you have any ideas? Oh,
I suppose it's somewhat analogous to problem 2, maybe.
yes. Please, use. Yes, yes, it's connected. Find the same criterion for k3 numbers and use it, and sum it over n less than x.
Well, maybe the criteria for Murray is that this, well, let's take the sum from the second problem and swap d square to
Yes.
z to k.
Oh, thank you. Yes, the criterion is just yes.
So the obvious generalization of the second problem is that this sum over d to the power k divided by n is indicator function of k3 number.
Yes, a serial arrays. It has the same proof. We can take the k. Okay, now you can count the numbers, k3 numbers. How to write it in using this?
Sum this for all n.
Yes, maybe you can write or someone who wasn't near Blackboard. Maybe you can write.
So we want to find so this is some something like that. So
N is less than. Yes. Mm-hmm.
so this is actually minus that times
Yes. Now we can do the same thing. I mean, yes, we can write it in such way.
so that's actually
So here we gain a lot because we replaced a very long sum of all n less than or equal to x by a short one of all d less than or equal to the root of x.
Yes, now the sum is short.
Fewer terms.
so
Yes, yes, yes.
so this is we will divide it.
Yes, we have two big sums now. Mu. Okay. Now, no, this is nice formula, but we can go further. For example, this one, this is small comparing with this. Can you estimate this? Give some upper bound. Maybe you can use big O notation. So each summand is has modulo less or equal than 1. Yes. So this is big O of what? Yes. Yes. Yes, it will be enough because now we will estimate this part. Does everyone remember what big O notation means? Here, of course, the constant is just 1, but it will be useful in other problems that we use. Here, no. We do not use anything here. This one? Yes, because we have. Oh, you can explain.
Because this is between
All the summands are big O of 1. Yes. And now let us compute this one. And here is a nice trick. We can write this as a sum over all d. You see, we have d to the power k. K is 2 or more, or bigger. And so this sum over all d, it's converged. And let us write it as a sum over all d minus sum for d bigger than k root of x. Okay? Maybe you can drop. Maybe you can drop x and just estimate the rest because x is multiple of all the sum. You can write here. Yes. And don't forget x. Okay. Okay, and I think you. Yes, we should keep this term also, remaining term. Yes, and this is a nice number. Who knows what this number is equal to? Who knows what its number is? No, it depends on k. So let me. Do you remember what is the inverse of zeta function? It's Dirichlet series for what? Okay, let me remind you again. Yes, of Möbius functions. So, and here we have Dirichlet series of Möbius function for s equal to k. Yes. So this is what? This is zeta of k to the power minus 1. Yes, okay. And actually, you see, when k increase, this tends to 1. And it is clear because less than x, all numbers are k free for k large enough. Yes. Yes, yes. So this tends to 1. Does it clear why this is z of k to the power minus 1, or I should explain again? Okay. And now we should estimate this sum. Who has any idea how to give it some estimate? We no, it's yes. This is trivial. Just estimated this by 1. This is sum over d more than k of x because of 1 over d to the power k. Yes, and this is because of sum. I mean, yes. Yes. And this is easy to estimate. Do you know how to estimate such sums? Yes, for example, to compare it with integral.
I don't know how to integrate.
Here, who knows how to do this?
+1 or -1.
Can we just integrate this?
I mean, okay, let me write it.
Let's replace k fruit by some
Yes,
parameter.
I mean,
Let's evaluate the sum over
it
k
is.
Петя,
А?
давайте заменим.
Здесь стереть, да?
Корень степени на t больше, чем t просто.
Okay, maybe it will be somehow clear, more clear. And this is less than integral from t or t minus 1, it does not matter, to infinity 1 dt over t to the k. Yes? And this is t to the power minus k plus 1 divided by k minus 1. Yes? But this k doesn't matter. We have k fixed in our problem. It will be in Bicol. Yes? You have the same. And you need to replace t by k fruit of x, and we get what? X to the power minus 1. Is this? Yes, and what's this? It's this is because of x multiplied by k fruit of x to the power minus 1 multiplied by k fruit of x. Yes, and now we multiply this by x, and we get again because of k fruit of x. So now we can write asymptotic formula that number of k3 numbers is x multiplied by zeta of k to the power minus 1 plus big O of k fruit of x. Yes?
So not only the density of k numbers goes to 1, the error term also gets smaller and smaller as k gets larger. By the way, studying this error term for various values of k is actually
Okay. Next problem is a bit similar. Who can solve B on Blackboard? Please, someone, Misha, can you solve problem for B, please? We want to find an asymptotic formula for the number of pairs n m less than x such that n and m are relatively prime. Transform this into some nice sum. And we have a characteristic function of 1 in terms of Mobius formula. Okay, we sum over and
Something like 2, 3, and 3, 2 separately.
2, 3.
Well, like
What do you mean?
if we change n of them, just replace
This is a symmetric condition. So what do we gain from changing n?
well, we can't.
We have sum over all pairs, and what's the condition that n that the
We can fix n bigger than m.
And then we will suffer. Let's not suffer.
so this is what's the condition that the greatest common divisor is 1, that sum over d which divide the greatest common divisors mu of d. This is characteristic function. Okay, and now we can change the order. What does it mean? Does it divide n and m? If and only if. Yeah. One here, yes? This is a set. We want to estimate asymptotics. How many numbers are here? This is not a sum. Huh? Yes. It will be 0 if n and m are not relatively prime, and that's what we want. Okay, and here it is. We can compute. Oh. Yes, let us think that yes, this is that pairs are ordered. D square. No. Okay.
So you see, we count the number of pairs n and m less than or equal to x, such that d divides n and divides m, which is of course an independent condition for n and m. So this is just a product. Right? What do we do now?
Mhm. Yes, so we have three summons, yes, if we open brackets. And two two last summons are just remaining term. We can uh, yes, and square here. So the main term is this one. Could you write it separately, please? Yes, sum over d less than x. Okay, and now we should estimate last two terms. Yes, we can estimate them both simultaneously, for example. Mhm. Let us write this in big of what? So we can sum them easily. Let me suggest x over d. Just x over d. Yeah. Is big of 1, and x over d is big of is yes, it's larger. And that's all. And now you have sum over d less than x, and what it gives us? What is what we get if we sum 1 over d less than x? So we have such yes, you can integrate. We have big O of x sum over d less or equal than x 1 over d. How to estimate this? Yes, it's logarithm of x. Do you have it on lecture or not? Sum over n. Yes, yeah, I think it could be. Okay, so this is because of what? X log x. Okay, this is and now maybe so here is this is x over d. Yes, this is big O of 1 mu of d, and we sum over d less than x. And now we should estimate this, and with the same technique, just we have sum over all d minus sum over d bigger than x. Mu x, maybe write x here. It's x square. D square over all d. Oh, yes. And now compute. We can switch Blackboard. can write here. This is because what? Some 1 over d square, it's 1 over x, yes? Yes, yes, because we have some d. It's estimated by integral 1 over t square, integral from x to infinity. And this is 1 over x. This is Bikov one. Yes. And finally we get x square, and what's this constant? Zeta of 2 to the power minus 1, yes? Plus big O of, what's this? This gives us big O of x, yes? X squared multiplied by 1 over x. Big O of x, and here x log x. So we have this, yes, full function for d from 1 to infinity. And who remember what this is equal to?
It's like p over something.
Yes, p squared divided by 6. And so this is 6 over p squared. Pi, yes. What's the question? We compute this asymptotics of this set. How many? Yes, we compute this sum d less than x, and we write it as the sum over all d minus sum over d bigger than x. This sum over all d is this one, and big O of x is this sum, and yes, maybe. Okay, so we don't have. Yes, we compute here this sum, and in the final answer, of course, we have x log x. Yes, the biggest term. Let us skip c and d. We have. I wanted to speak about problem 5. Yeah, we have 10 minutes. But let me give you a how to solve number c. Maybe you can think at home. Sum over all n, phi of n. And here's the trick. Maybe you know that sum over all d that divides n, phi of d is equal to n. Who knows this formula?
This is an unelegant way to do this.
Oh, but I love this way.
Actually, an unelegant way after we did B, because you can just use a definition.
Okay.
So the ultimate hint here is that you already know B, then you can deduce C from B.
Yes, okay, so I did not notice it. Thank you. Yes. Okay, D is, you can try to do D in the same way using this formula with Mobius function, but you will, there are some obstacles, but yes, some complications. But you can try it.
With the
Yes. Now let us solve problem 5. Maybe we can try to solve it and you'll see. Maybe we can move it to the another problem list. Yes. Problem number 5. Do you know what is zeta function when s tends to 1? How we? Yes. So you know that. Yes, yes. So zeta function is holomorphic, and yes, meromorphic. It has one pole at 1. And what is its Taylor expansion at 1? So first term. What is the residue at 1? One. It is 1. The residue is 1. Yes, it is 1 over s minus 1. Plus big O of 1. Yes.
Yeah, I actually proved that this big O of 1 starts with gamma.
Yes. Okay. And we now speak about problem 5. We want to write some asymptotic formula for some p to the power minus s. Here s, of course, is bigger than 1, but close to 1.
Yeah, s goes to 1.
We want to prove that.
When we write sum over p, this means that we sum over all prime numbers.
And I want to say that this formula implies this formula somehow.
Any ideas how to do this?
Yes.
Anyone? What do we know about zeta of s?
Yes, but we don't know the connection of sum over primes, and here is the sum over all natural numbers. Yes, this is the idea. Maybe you can do it. No, you can, if you want to stay. Sum over primes, yes. Huh? Here's sum over primes. Yes, logarithm of product is sum of logarithm. We write this for, of course, for real part of s bigger than 1.
Let's write big O after this.
Yes.
One term and then
Plus big O of, this is the remain term of big O of what? 2s, yes. You can actually, yes, s is bigger than 1, you can write this here p square, yes.
correct? So the expansion of minus log of 1 minus x is x plus big O of x squared, right?
This is just Taylor formula in piano form, yes. Yes, constant is for logarithm. It's absolute constant. It does not depend.
Да. Значит, тогда
Uh-huh. Yes, this is big of 1, of course. Yes, because it's converges.
это, наверное,
It converges. It doesn't matter. It's big of 1.
ну, допустим,
It doesn't matter. Yes. Yes, and that's the solution. And now you can take logarithm of right part and to get this. We have.
So if you consider the Dirichlet generated series for indicator function of primes, then around 1 it behaves logarithmic. So for example, there is no hope of this robotics at all.
And also we see that sum of one over prime, sum over primes, that it diverges. Yes? And problem 5b, I think should be not hard. Who see why this is true? Does everyone remember what this means? Yes?
It's the same as
Because yes. So f is less than g. It means that f is because of g, and it means that modulo of f is less or equal than g multiplied by some constant. For example, x large enough in our case. Okay, what is P is yes, let me write first such inequality. P less than x, 1 over P. I want to say that this is less than the same sum, but 1 over P to the power 1 plus 1 over logarithm x. Do you see why this is true? А? Что еще? P меньше x.
Промежуточная штука. Это промежуточная штука. Да, все понимают, почему это похоже. Кто понимает, как имитировать?
Just because the power is bigger.
each summand is
Yes, P. What is P to the power 1 over logarithm x? It is first. It is bigger than 1. Yes. And also it is less than x to the power 1 over logarithm x. And this is equal to what?
Что такое x степень 1 на логарифм x? Быстро. X степень 1 поделить на логарифм x.
What is this? This is not number theory. This is okay. It is exponent of what? Huh? Yes, this is yeah. It is Euler constant. Because this is e to the power logarithm x, this is x, to the power 1 over logarithm x. This is e to the power 1. Yes, yes, e. Okay. So with multiple, we have less than here because with multiple does not change anything. And now we have a sum over p less than x, but now, of course, this is less than sum over all prime numbers. 1 over p to the power 1 plus 1 over logarithm x. And we know the asymptotic of such sum. Let me rewrite it quickly. What's the asymptotic formula? Use previous use. Yes, what is this here? S. No, use 5a, previous problem. 5a. We estimated sum of p primes to the power minus s. Yes, and what our formula gives us? This is equal to what? Logarithm of
1 divided by of just logarithm x.
Yes, this gives us logarithm x plus bq of 1. And this proves that such sum is less than double logarithm of x. Yes? This?
Да, там у нас что получается? p в степени 1 плюс 1 лог, которую мы к чему?
We use 5a. 5a используем, подставляя s 1 плюс 1 на логарифм x. Она как раз говорит про такую сумму. 5a. Actually, are there any other questions? I think. Which one? This is logarithm zeta. So we can write here logarithm of this is equal to logarithm of this. And zeta is such product over primes. And logarithm of this is this one. Okay, actually, such sum is it is asymptotically equal to double logarithm. So so we get a good upper bound, which is actually the best we can have. It means that if we divide by log x, it will tend to 1. Yes, it is. Yes, equivalent, asymptotically equally. Yes, and this is called Rankin trick. Here we made our sum a bit worse. We added this, but after that we could extend our summation to all primes and to get some, because now it will diverge. And there are some other situations where we can do the same trick. Okay, that's all if you have questions. Как это выключить?